Well, thank you everyone. So, as presented, I'm Théo Madzou. So, I am co-founder and CTO of a Web Studio, we Web3 development agency. So we've been working in France for since 2021. And today I'm going to be talking about something that's related to one project we've been building and the tools we need for this. So essentially the building blocks for electronic identity verification. Now, work. And why am I supposed to point this out? Okay. Let me do it with my computer. All right. So first, what is an electronic ID? Who knows what that is here? All right. Good. That's probably a pretty good number. Oh, so thank you. So even if you don't know what it is, you probably already have one. So it's actually quite common, but most people don't know that it is. So for example, passports, a lot of them are. So this is, for example, a bunch of different passports. You got like Australian, British, French, Chinese, different kind of passport. And all those, they got this little icon right here. And this indicates that it's an electronic ID. What it means is that I got an electronic chip in it that you can actually read. And it applies as well to ID cards too. Start to spread in ID cards, especially within the EU, but other countries as well. And it's standardized by the same body. So this body is called the International Civil Aviation Organization, which is an entity from the UN, the United Nations. So they do all kind of standardization around that are needed for aviation, for the travel, and specifically they set the standards for travel documents or identity documents. That would include passport, ID cards, also visa, residence card, and others, like less common travel documents. And so this is supported by a lot of countries, virtually all countries, and specifically for the electronic ID, it's like over 140. So this standards covers both physical layout and the electronic chip itself. So physical layout, that would be stuff like what security mechanism you want to prevent a counterfeit. Like for example, some element that are not only visible under infrared or ultraviolet light, those kind of stuff. And it's even supported by countries you would not expect it, so, such as North Korea. They don't issue a lot of passports, but when they do, it's actually compliant. So what about the chip itself? So this is really the part we're really interested. It contains quite a lot of information that's quite useful. First of all, everything you see on the ID card or on the passport visually is going to be contained in it. As well, it contains some information about the authentication and security mechanism in place because you kind of want to have some things safe with this. And as well, digital signature, which is a very important feature that I'll talk about more in detail later. So you can use to verify the validity, authenticity of the document. The main data, what we're really interested by, is divided in what we call data groups, up to 16 of them, and each data group is a given theme, like a given topic, specific one, and only 2 of them are mandatory. And the 2 that are mandatory, that's the first one and the second one. And the first one contains the machine-readable zone, which is the 2 bottom line at the bottom of the passport page, or the 3 bottom line at the back of the ID card. And the second one, the photo, your photo that you see on your ID, this is contained on the second data group. All the others, the 14 others, they're optional. Doesn't mean that they don't contain interesting data, but it means that you should not expect to be in every single passport you see. So it's optional. Notably, you have data group 3 and 4 that contain fingerprint and iris, but that you're not going to be able to read it because most of the time it's behind another layer of authentication that only authorized personnel can read, like at the borders. And DG11 that contains supplementary information, essentially what you see on your passport data page beyond what's contained in the MRZ, like the machine readable zone. I'm going to talk a little bit more about the MRZ later. And this data is rather easy to access. So it's an NFC-enabled RFID chip. It's very small, you don't really see it in your passport, but somewhere you can read it, with essentially any device that's capable of reading NFC chips. So like a smartphone, which is the case of most smartphones nowadays. Now the question is, so you can read it really easily, so do you think there would be a problem that having like such information readily accessible and readable by the smartphone? Like, it might be a problem. So this is why you have a restriction mechanism. So you do control the way you access the chip data. So you have like two kind of access control in place. The basic access control, which is the older version that's been in place for a longer time. It's present in all documents. That's been issued before 2018. And it's only based on symmetric cryptography, purely symmetric cryptography. And PACE, which is password authenticated connection establishment, which also leverage symmetric cryptography with a Diffie-Hellman key exchange to generate ephemeral session keys that you can use to encrypt the data. So what it prevents essentially is what we call skimming. So let's say you have, like, for example, your passport, ID card in the back pocket. You're in the metro, someone comes with his phone, so you don't want him to read that data without your consent. So that's what it prevents. And also eavesdropping. So when you have two devices, the device is authorized to read the chip data, but then you're gonna have like a bunch of information that's gonna be exchanged between the two, and you don't want that to be fetched by somebody else that's nearby and just get the data. So what you do is encrypt it. And the way you authorize is through the MRZ, which is why it's important. You have data contained in it, like the date of birth, date of expiry, the document, and document number. That allows you to derive a decryption key and encryption key that you can use then for the rest of the protocol, the back or the base. So the assumption is that you need to open your passport in order for people to actually access the rest of the data, or like flip your ID card and show the MRZ. So here's an example. On the right you got like a passport, like this is an Irish passport. Like for information, all those like are specimens, so the data on it is not, this can be public. It's from the Prado. It's like a public register of like different ID documents, so that every state is aware of like what kind of other documents they issue. So on the right you got the Irish passports. On the blue, in blue is like the document number. You can see it on the top. That's also contained in the MRZ. Then you got in red the birth date, and in black the expiry date. The dates are encoded in like two numbers for the years, and then the rest is classic, like 2 numbers for the months, 2 numbers for the day. And ID card, same thing. It's just on different lines, but you also have the same data, and the rest of the data is on the front card, so you don't see it. Essentially, this is what you use to derive the decryption key and encryption key for the communication and the authentication with back and base. Now, you can also use another number, which is called the card access number, but it's not on every document, so most of the time you use this. And it's engineered in such a way that's easy to read with OCR, so you can easily like get it optically, automatically, and to derive the key. So, now we got all the data. So what can we do with it? Well, we can verify the signature. So as I mentioned, there's 2 digital signatures in it. So those signatures, they're what allows us to verify the authenticity of the document. So how does that work? So who's familiar with the X509 certificates here? All right. So those are like the same kind of certificate used in SSL, like certificates. Essentially, it contains some information about the authority that generated the certificate, the public key that was used with the private key that was used for generating the signature. And in this case, you have like 2 certificates, the document signer certificate and the country signing certificates, CSCA, that are X509 certificates. The first one, document signer certificate, sign the data of the passport. So you have a signature over the data of the passport, so you can check that the data has not been tampered with when you can check it against public key. That same certificate is stored in the passport chip, so you can easily retrieve it. These same certificates, data is signed by the root certificate over here, our trust anchor, which is like the root certificate of the state. So whatever is signed by this, you can assume that it was signed by the state. So you assume that only the state could have known that private key behind, and so you can be sure the document is authentic. So essentially what you do is you verify those two signatures, and you're able to have like a proof of like authenticity. And you can do this within a ZK circuit, which is the powerful thing here. Any question here? Just.
Can you specify which kind of data is signed? So I know that in some documents they don't sign the identity attributes, but only basically a statement that this chip is trustworthy, and then the actual identity data will not be shared in a signed way, but just in an authenticated channel to avoid like selling the ability to sell verifiable data.
I actually think this is just after I was describing like what kind of data is signed, like on this side. Like I will describe it just a bit later. Any other questions? No? All right. So the first signature, so it's all of the document data. What is exactly? So the data group I've described before, they have hash of every single data group. And you then combine together, rehash again, and then you add some padding that contains information about the signature algorithm, the date of signature, and then this is the message you actually sign. From the document signing certificate, this is what it actually signs. So those data group. The rest of the data in the passport is not signed, so it's only that. So you're gonna have the photo, you're gonna have all the MRZ, you're gonna have the personal information, the security mechanism used, all this is signed. So this is the signature and hashes are stored in the chip in what we call the SOD, the document security object. And what you want to do essentially is that you want to recompute the hash of the data you use. So like for example, let's say you want to get the date of birth from the MRZ. So you get the date of birth and you also recompute the hash of the data group 1, making sure you use the same hashing algorithm, because it can be different ones. And then you combine it with the rest of the hash, because you don't need to recompute them if you don't use the data. And you make sure that the end signature, like the message you just generated, is verified against the signature. So that way you can use data that you know for sure has not been tampered with. So this is the assurance it gives you. And so the hashing algorithm, as I mentioned, it can be any SHA. So quite often it's going to be SHA-256, but sometimes it can be SHA-1, SHA-512, SHA-384, sometimes maybe any other, but like those are the ones I've seen so far. So you kind of have to adapt, which is a bit annoying sometimes. And the second signature, so the one I mentioned, so before with the DSC data, so like the data, what we call the data to be signed. So everything in essentially nearly everything in the certificate beside the signature that's been generated before is signed by the root certificate, by the private key of the state. And so it contains the public key, so you can check that the public key you can check the public keys in the message, then verify it against the signature from the public key of the state, and you can make sure that indeed that certificate was generated by the state, and you verify that that certificate did sign the data, so that way you completed the trust chain, and you know that the state signed that passport. Yes?
You also consider the revocation of OCP, CSP responder in general revocation, because it can be signed and revoked.
The location of...
Revocation list.
Oh, revocation. Yeah, you would need to check the revocation list as well, because you can have documents that have been lost, stolen, or like someone just want to revoke it, like a state, like say that person, we need to revoke that person, so you would need to check against the revocation list as well.
But there is an issue here that for some states it's not provided as a list, but as a server.
Oh yeah.
There is a responder.
So this is actually a problem also for the public key. This public key, the CSE certificate, is also not available sometimes. So this is a problem with some states. They don't give you the revocation list, and also they don't give you the CSCA certificate. So you cannot validate the authenticity of the document. So with most, I think all European countries, they provide the CSC certificates, and nearly all of them provide the revocation list. But like, let's take, for example, Africa, most of the time they're not going to provide any of it. So you cannot actually validate the authenticity of African passport most of the time, which is unfortunate. But the ICAO is pushing to make it like more public. So they have this master list that contains all the CSC certificate and sometimes the revocation list. So they do make an effort to make it more public, but for now it's not complete.
I mean, the problem is not only the fact that it is public. Even in Europe, it can be public, but provided through interactive services like OCSP responders. So in that case, I'm not sure. I just say I don't remember the details. I'm not sure what can be done if you can still do some zero knowledge public verification. Because you should contact online. Yeah. In Italy, it's like this. For digital identity card, it's like this. You contact online some service, some server, and the response if the certificate is okay or not.
I'm trying to think as like to generate a proof from this. So you kind of have to trust the service that you would need the entirety of the list of revocation list, not an interactive process where they just answer you whether it's true or not that the document was revoked. You need the entirety of the list to be able to pass it as a public input and generate a proof that it's not part of that list. Otherwise, if you don't have the entirety of the list and you only have an interactive process, then that won't work. Or at least you have to just trust the provider, which is not that good. Any other question regarding this? All right, I'm going to carry on.
Are the hashes somewhat blinded?
The hashes, wait, no, I don't think so. This is just basic like hashing with the bit of padding I mentioned. There's nothing else.
So if you see like the other hashes needed to recompute the root, you could infer like the date of birth with a biometric.
I never studied that, but probably talk about it like later because I wouldn't be able to know. And so all this, the point is that we can do it within a ZK circuit. So we verify the signature. So essentially, the passport data, we pass it as private input. We verify each signature, like the process I've just described within the ZK circuit, and then we can expose the data if we want. So that way we keep the passport data private, but we have a proof of identity that's very credible. The one thing, what do you think needs to be public in terms of input? Like for the verifier, what do you think the verifier needs to actually pass as public input to have like a credible proof for him or her?
The key?
Which key?
Of the signer?
Countries.
Yeah, the public key you mean?
Yeah.
Yes, yeah, you need to pass the public key of the CSC certificate as a public input. That way the verifier can get it from whatever source he trusts. So for example, the government website or like the ICO master list, so we can verify for sure that was indeed that certificate. Yes?
Timestamp and the random challenge?
Timestamp, yes. Random challenge, so when it comes to, you're mentioning nullification, because I'm not going to mention this, but
I was rather thinking about replay attacks, where maybe at an earlier stage you reveal some of the signed data to an authority already, and so they could also create a proof because there is no secret involved.
That's a good point, but I never thought about this, yeah. Okay. So, now a question. What do you think you can do with this? What kind of proof can you generate? Like what data do you want to expose? What use case do you see with this? Yeah?
Prove your name?
Prove your name, yes, like your official name. Like for example, have you used LinkedIn? With Persona, there is the data from your chip, so regular KYC provider. What it does is read the chip and verify that your name on LinkedIn equals your official name. So that way you can't fake your name. That's a good example. Yeah?
Proof of age?
Proof of age, yes. So you can prove that either you are a given age or you are above a certain age. So you don't even reveal your age, like over 18, over 21. So you have like full privacy, no date of birth revealed. Yeah.
Yeah, I mean, for this application, I think there is an issue. I mean, it's like you implicitly have considered in the threat model that your document number is private. The point is that for passport, the document number, the information are somehow public, because, for example, you are requested many times to send your passport, the copy of your passport. And given the copy of your passport, anyone can forge the proof. So the problem is just for passport, because for electronic identity card, in fact, they are signing card, and you can sign just with the secret, the PIN. Mm-hmm. So in that case, it makes sense to consider the same process with the signature derived by the digital identity card, because this signature can only be produced using some secret that only the owner of the ID card knows. But for passport, as I sent to my company my passport, I sent to I don't know, many administration my passport, so anyone with that copy can forge the proof of name.
But I mean, do you send your passport, but you send like a picture of it, right? In this, like, like, how do you send it?
For example, when I went to a passport check in the airport, with the same information that the police says, could forge the proof.
Yeah. I mean, like, as soon as you hand your passport, essentially you hand authority over it. So, when you do it at the airport, they read everything. They could generate a proof with it if they want. There's always trust assumption. Identity is going to be hard to have a system that's fully trustless. You have some trust assumption.
For ID cards, you can do better, because for ID card, the signature can be done with some challenge, and you can only sign given some secret.
Are you referring to chip authentication or no?
Yeah,
okay.
Digital, like IDAS cards are also signing cards in Europe.
Yeah.
And for my card, I have a PIN to sign documents. Only with the PIN I can sign.
Okay. So they require a PIN to. Okay.
That's why it would make sense to have a challenge included in the proof request, so you can prove the ability to sign the challenge.
But this is proprietary tech, or is it like the ICAO specification? Because I know, because I've talked to the French Cybersecurity Agency, and they did mention they have a proprietary tech in the ID card that's separate from the ICAO specification. They're not going to give us much information about this.
So not proprietary in the sense that it's not open what's happening, but proprietary in the sense that it's not ICAO but a country-specific standard.
Yeah, it's like so that would be like country-specific, which is going to be a bit harder to implement.
Well, precisely in Europe is standardized, but EIDAS is called.
EIDAS, yeah.
All European cards follow this standard.
Yeah. This is a different standard. EIDAS says I've studied it as well. So this is different from the ICAO. But if you have this, yes, that would make sense to add your challenge you mentioned, because you will have like stronger security.
Yeah, because I think ICAO does not standardize it, because it's not the purpose of a passport to do online authentication. So it's not a security fault, because they only want impersonal when you go for them to the airport. For that specific security application, it's okay.
Yeah, technically they regulate more travel document than identity document. So the main point for them is traveling, not really. Well, you can identify yourself as traveling, but that's online is not their purpose. All right.
Sorry, maybe to continue your question about what the verifiers, what should be the public input.
Yeah.
I think in this setting, your face should be a public input. Like right. I can see you, I can see your passport. I can tap it, and then I can check that your age is what you're claiming to be. But I need to link like your passport with something physical about
so I will mention like face match before, but after, but as a public input, I'm not quite sure. I'm not quite convinced. You really want to have your face like shown every time?
Something like could be if I know your name for sure.
Yeah.
Then I can use this. But otherwise, you can give me the passport of somebody else, so it's kind of irrelevant.
Yeah, that we'll mention later. That's interesting you mentioned.
I think you're part of the verifiable, the public inputs of the verifiable.
All right.
And the expiration date would be a public input?
Yes, you could. Well, It could be a public input, but like I'm implicitly you would make the verification from the private input, and I think like having it as a public input could be useful in the case when you do full KYC, and you want to have like to know when the document expires. So you want to expose that, so you don't have to ask the user every time, so you know when it actually expires. Yeah.
Another way could be passing the public input to the current date, and then
Yes.
compare if that's expired or not at the time of the proof being generated.
Yeah, you do need like a public input the current date as well when you do proof of age as well. So that's often you need that input. All right. When it comes to the algorithm, the signature algorithm used, the specification of the ICO allows for RSA, ECDSA, and DSA. No EDDSA. And within the RSA, well, there's full flexibility in terms of like the key size. It can be 2048 bits, 3072, 4096. Those are the most common. But you can have others as well. The exponent can be different. Most of the time, it's the most common exponent. 65,000 something, I can't remember the exact number. But sometimes they use something else. For ECDSA, it could be any curve whatsoever. There's no mention of a given set of curves in the specification. So you're going to have like a lot of different kind of curves that are most often not widely supported in crypto or non-pairing friendly, which can be a bit of a problem. For example, Germany used Brainpool for their passport, like as for the curve, for ECDSA. And DSA, to the best of my knowledge, is not used. I haven't seen it anywhere. All right, so we can try, if you want, like signature verification with Noir. So you can scan the QR code and then go on your computer.
Computer or phone? Is mobile okay, or does it have to be a computer?
I mean, you have to do it on your computer because you would need to like clone the repo and then just run Nargo. Does anyone has already tried Noir before? Okay, this here. There's a bit of a setup. I don't know how good the Wi-Fi is here. Okay, because you would. Yeah, I didn't think about this because like you would need to download the entire SRS key. How long is this gonna take? I think it's 200 megabytes. 200 megabytes with 54 with that many people in the room. Yeah, I don't. Okay, maybe we're gonna break down the internet. That's worth a try anyway. Do you get the link? Hopefully. All right. Let me show it on screen. Yeah, I was supposed to only take 5 minutes, so I don't know if it's going to take 5 minutes, but I'm going to show it anyway. Okay, so where is it? Noir iOS optimized. There it is. So can you see it? It's fine, my screen, like the code here. So here you have. So this is like a signature verification with Noir. So this is. Let me just check I have the right version. So I'm going to do Noir up. V0 2022.
Do you mind zooming in the screen a bit?
Oh yes.
Thank you.
Okay.
Yes.
All right. Yes, that's a bit slow. Okay. So this is supposed to run with the version 0.22 of Noir. So essentially what it does is it verifies a signature, RSS signature. In this case, it's like 4096 bits. Yes. So that's a pretty big signature. That's the one that's, for example, used by the French CSS certificate. But yeah, I don't know if I'm going to be able to execute it. Do you have the code on your laptops? Because you can already check out the code, see how it looks. I have a little like question at the end of the notion, if you've noticed it. Okay, well, I don't think I'm going to be able to run it. Let me cut it. Just checking which version I have right now. Yeah, that won't do it. Yeah, Noir is moving quite fast. Like I can't use that version because there's been a few things that have been deprecated in this. So it's using like a big integer to manage like a big number for RSA, but this is based off like a library that no longer works in the latest version. I did make a new library, but for now it's like very not completely ready for use, I would say. So yeah, I guess we can. I'm just gonna make a little apartheid. So there's a certain assumption that's making this verification. I don't know if you can read it. Let me just show it specifically here. And I was wondering if any of you think that this assumption is safe. Because like in Noir we have like performance issue with like RSA verification. With Circom it works better. It's like a few seconds, but here we're talking minutes. So this one was an attempt at making like a improvement of performance. But there's a bit of an assumption here. And what do you think is safe? I mean, I'm just giving you 30 seconds to see. That's a bit short time.
By the last experimentation, do you mean like if you're raising it to the power of like 65537, you're like doing it to 65536 and then multiplying again? Is that what you mean by only the last exponentiation?
Yeah, so you would like only do that last one there. That's what I mean.
Okay.
I think it was safe with like a range check.
Yeah.
That you don't underflow
Don't underflow.
or overflow.
Wait, Michael.
Yeah, so it turns out that I think you were kind of heading towards that, where if you're just doing the final exponentiation, it means you bring in a whole lot of the value, and then what you can do is you can find the modular inverse of the public exponent, so the public modulus, and then you essentially allow that to kind of offset it so that by knowing what operations we done in the circuit, you can apply the modular inverse of that in what you pass in as your like partially different signature, and then you can effectively get anything you want as a result. So it kind of breaks down. You need to always use the original signature and raise that to the public square root of 55,000. So it was kind of nice in theory, and it's way more efficient, but if you're partially different signature, it's not going to work anywhere along that exponentiation.
Yep. So it's not fully safe, but I did the job for a little while, but now we need to find another solution. But like there's a full RSA verification library in Noir, but like the performance is so bad that I'm not even going to try to run it. So that's why we had this. All right. Did anyone manage to do anything? Oh, you run it. So you were able to run now the proof?
Yeah, I got some new file that's called RSA optimized.
Yeah. Okay. Well, that's good. This one person managed to do it. Oh, you did? Nice. So you already had Noir installed before, like Nargo? And you just installed it now? Hey, so why? Okay, I guess we don't get the same like broadband speed one. It's a bit weird. Wait, let me get it.
There is a warning though.
There's no what?
Just a warning. And also use expression.
Oh yeah, the warning, I like it, so it's okay. Alright, so let's continue. Use this. Oh yeah, I already went through this. So when we talked about the different proof we can generate. So like I was mentioned, age threshold, citizenship, residence, because you have proof of like, you can have like Residence cards are electronic too in some European countries as well, so you can prove that you're resident. And also sometimes you have a piece of text that tells you that that given person is allowed to work, so you can have like maybe a proof of ability to work in a given country. You have like personhood from a valid ID. There's a bit of like a caveat here that we'll mention later. And for KYC, so you reveal a bit more data, like for example, date of birth, date of expiry, first name, last name, that you would need for full KYC. In the case of full KYC, there's also AML and CTF to take care of, which is a bit of a challenge, but there's a few things to go. You could generate a proof that you're not part of a sanction list. Like you have the public one, OFAC, EU, UK, UN, but you have a lot of proprietary lists that are not public, and you need the entirety of the list to generate that kind of proof. So that would be a bit of a problem. But maybe we can try to talk to those like companies that hold those proprietary lists and ask them to generate proof for us. But I don't know how that would go. So this is the problem we mentioned before. So what if I have someone else's ID? Can I generate a proof and pretend to be him or her? Well, what do you think? Yes. Yes, you can. So how would you prevent this? Like, what's the way to do this? Like, think, for example, the current KYC provider. How do they check that it's you on your passport? What do they generally do? I guess you've done some KYC before.
Picture, biometric.
Yeah, picture. Like some video where they ask you to turn your head around a bit. So check for your aliveness, stuff like this. So yes. So you can do this with an ML model. So you have like an ML model that's able to take your face as input, your video, and then check for your aliveness, and also check that, for example, the face, in this case of the passport, the photo, can resemble your face on the video. So you can that way make sure that the user is the one, so on the passport, the one that generated the proof. So now, if you want to keep this private, we're gonna need something I know some people are not always like fond of, which is ZK11. Yes, ZK11. Such a nice thing. Like a lot of people use that mostly like for the context of like just a proof of execution that everything was executed correctly. But like here we wanted specifically client side for privacy. So essentially you execute the model locally, so that's already a bit more constraining, and you need to generate proof of execution of the model by having its input private and the weights public. And the weights public is fine. I know that some people don't like to have that, the weights public, but we kind of have to here. So, and you combine this proof with the proof of valid ID, then you have like a strong credible proof, like a stronger credible proof. You can't pretend to be someone else as easily. There's some people that are very good at it, like intelligence services, but let's see how far that goes. So, client-side ZK11 is going to be expensive. So this is not LLM. This is the paramount of like big models, but this is still not that small. So you can imagine running this maybe on a pretty good laptop, like a MacBook Pro. But remember here, we're reading from a phone. We don't want the data to leave the phone, so what does this mean? We need to generate the proof on mobile. And we need to do ZK11 on mobile. That's a challenging problem, isn't it? So we need very efficient mobile proving.
Maybe before we go there, my question is not about efficiency, but about security. So your model is open source, and
yep.
It's not hard to generate essentially videos that will pass the model. It's shown that you can generate adversarial examples that will fool the model and classify you as you, even though it shouldn't do this. So like ZK11 doesn't prove that the actual ML is secure, and ML is proven to be insecure.
So how would you go about it? So because would you make the both private?
You cannot make the model private because as long as you can access it as a black box, you can still extract the model. So there is, I don't know of a solution right now.
Go ahead.
To reiterate, a bunch of European cybersecurity agencies have basically forbidden the use of passport plus liveness check with a face for health applications exactly because of this issue. So basically without using cryptography, like a private key secured in the secure element, you will have a hard time getting to a high level of assurance according, for example, to the EIDAS regulation.
So yeah, I talked to the French Cybersecurity Agency about this, and they told us they do not accept any kind of ML model outputs as a proof of liveness. It has to be a manual check. Like, this is the state of what it is. Like, they say they were too disappointed by the results of the ML model ability to check that person was real or that did match with the person on the passport or the ID card. So that's a bit of a problem. But definitely, you can use the private key on the card, but that doesn't solve the problem using someone else's.
It does.
With the case of the PIN, it does, I guess. When you have
exactly. So that's basically the second factor that most ID cards, or a lot of ID cards in Europe, like the German one, built on, and so they get higher level of security.
Yeah.
Because you trust the secure element that it only signs anything once they get the right PIN.
Well, I actually don't have an ID card from France. I should probably get one. But they have an application that read the data from the chip of the ID card, and I think they have a PIN too. So that might be the same thing as the German one. So that might be a solution, but that's kind of a little bit less elegant than face recognition, because you have to just rely on the password again. But yeah, I guess you could all have all the solutions. All right. Any other points? Remarks?
Any comments on that point that I made?
Yeah.
About security of ML?
Yeah. So regarding the security, you really don't think you can make both the weights and the input private?
It doesn't matter. So there was research shown that even if you make a model, you can access it for inference, you can still extract all the weights from it.
Yeah.
Okay. So
Yeah. All right. Yeah, so if you want to try, we're gonna try a little bit of mobile proving with Noir using React Native. So for this, you need a MacBook and an iPhone. Well, at least the MacBook you can build it. For iPhone, you need the iPhone to actually run it. But I can show it just real quick. It only works with iOS for now. There's no way of doing Android mobile proving with Noir. With Circom, you can do it with the tool called MoPro, and actually Oscar was behind this, will make a talk soon, so if you want to check it out, you can go that. But with Noir you can also do it, but the performance is not as good, but you can do it still on iOS.
There is even an ARM assembly prover by Polygon.
On Circom?
Yes.
Yeah. Okay, they got a lot of different kind of provers for Circom, this is much more support for Circom than any other DSL that I know on mobile. But mobile proving is still a very niche area of ZK that needs some founding, some focus. That would be nice to have, because the thing is that in the case of ZK, it's been motivated a lot by blockchain. So what they care about is really the verifying time to be as cheap and fast as possible. But here we really want to have cheap and fast proving time, even if it's at the expense of verifying time actually. Oh shoot, where did it go? There it is. So I have Xcode here, so this is the project running in Xcode. I'm gonna choose my iPhone right here. You can deploy wireless, which is very nice. And I'm gonna run it. Shoot. It's not the right screen. Alright. This is the nice thing about macOS. You can show your phone like this. Very easy. But actually I can't see my screen anymore. I can see whether it's building.
So is this WASM based?
So the way it works, so actually it's Michael's library here behind. So I built like the boilerplate for Noir with React Native. I use like this library called Swar, which allows you to generate proof on iOS, which is based on NoirRS, which is another tool from another guy called Bartosz. And this used directly Bartenberg C++ code as a base for actually generating the proof and not the WebAssembly. So it does have a disadvantage that when there's an update of Noir, then you need to, well, kind of get it updated to the new backend, which comes with problems.
I played around in Circom also with WebAssembly, and it was quite unstable. So once you go to like Rust or C, it's much better.
Okay. I'm going to do it without deploying.
No, just a small question. But which component doesn't support the ARM architecture for this? You say?
So essentially, it cannot run. What I mean is like it cannot run the simulator because the simulator is like a different architecture than the iPhone itself.
I didn't get that, sorry.
So you can't run this on a simulator for now because it's a different architecture than the iPhone itself.
Yes, I mean, why? Which component from all this does not support?
This is specifically Swarenberg, so like the library behind that allows you to generate proof that doesn't support. Yeah.
Currently, the targeted architecture says Apple Silicon Mac OS, and then there's going to be support for Apple Silicon Simulator, which is slightly different. That'll be the next version as well. But currently, it's just Mac OS, Apple Silicon. Oh, sorry, the other way around. iOS, like the actual device itself.
Great. Wait, let me see if I can get it running. I should probably use a cable. Oh, there it is. So this is the example running on iOS. So I can, wait, use a cable. Has any of you been able to get it built or run on your own side? No one? Okay. Oh, wait. Oh yeah. Okay, that was a Alright, so now it should work. So this is simply like taking two factors of to a product. So those are two private input. The outcome is public. You generate a proof. So this is on mobile. And here you have the hexadecimal format of the proof, a bit truncated because it's a bit long. And you can also verify it directly from the phone as well. Alright. I don't know why, but it gets blocked on the pop-up, but yeah.
Sorry, would you mind commenting on the difference between Mopro and Rhino Noir?
So Mopro,
like the actual practical difference, if any, besides efficiency?
So Mopro is specifically for Circom, while in this case it's specifically for Noir. So that would be one of the main difference. Apart from this, I know that the guy from Mopro wants to support others like Halo 2 or Noir, or both. But as for the technical differences, I wouldn't be able to exactly tell in details. No.
I guess also one is running on React.
No. So like
and
this
the
is
other one is.
This is I could make a boilerplate with React with Mopro as well. You can use the way React works, React Native, is that you can connect to native code like Swift and Kotlin on Android. So whatever works with the native app, you can make it work with React Native, which is essentially what I did. Like most of the code here is actually in Swift. Even I have some JavaScript, which is the main point of React Native, but most of the logic, all the logic for generating the proof is in Swift. Any other question?
I have a question. Like, would it work on a web app using WebAssembly, for example?
This?
Yes. Not using React Native, but using just web application.
Oh, web app is much easier because you have like the tool. Noir.js works just fine on web. Like this is a tooling directly from the Aztec team. So mobile web has a better support than mobile for sure. But like here, since you cannot use a web app with this use case because you need proper NFC API, and the web API for NFC is too limited to be able to read data from passports. So you have to use a native app, which is the bit of a limitation here. So wait, do I have an Android folder? Yeah, I think I didn't remove it, but yeah, I was trying to make the implementation for Android, but with Bartosz, like the guy that helped Michael do the Swarm one, but we kind of got blocked by an issue with linking when we tried to target like the Android architecture.
So that'll be the next version as well.
Wait, did he make that guarantee? Okay. Well, let's hope it's gonna be. Let me deactivate this so I can switch back to my laptop. Alright, so where is it? Alright. If you want to check the circuit that I've done for the project, which is called Ocelots, it's in Noir, so you have like an idea of like the different steps you make in the circuit. So that circuit basically works for a French passport. There's like a few things that need to be changed if you want to support all the passport, because there's a padding that changes, the hashing algorithm, so the size of the array changes. There's a lot of dynamic thing, which in the ZK circuit makes it rather difficult. So this has been tailored specifically for the French passport. So I've been able to generate a proof with my French passport. And it verifies the age, and it can verify also the citizenship. Actually, regarding the citizenship, I was wondering, because like that would be an interesting question if anyone can come up with a way around this. If you want to prove that you're not citizen of a given country, how will you do it? Because let's say you have a passport that's from, let's say North Korea. You use it, and you say that people from North Korea are not allowed. Well, the proof would not be able to be generated. But what if you have another passport from another country? Then you can always generate it from that other country, but you're still like a North Korean citizen, and that would be a problem. So that's the one thing I was wondering. Yeah, go ahead.
I guess I would arrange the signing authorities' public keys like in a sorted Merkle tree, and then you can do a proof of inclusion or exclusion if you want.
Yeah.
So inclusion by just Merkle proof verification in this CK circuit, and exclusion by verifying two adjacent Merkle proofs and proving that basically the public key you're referring to is in between.
The public key referring to...
So the public key associated with the signer of the document.
Sign of the document.
Because basically you want to prove that the public key who issued the document is included or excluded in a certain list, and so you could refer to like a sorted array of issuing public keys.
Yeah, but like my point is that you can check that for a document, but like there's nothing that prevents a person from having several documents from different countries. So if you do the proof for that given document, okay, but that person might have citizenship of another country that's not sanctioned, in which case he can evade the proof. And it feels like it's a physical constraint that you cannot go around. There's no way around it unless you have some kind of centralized system. Yeah, so there's no neat solution for this, unfortunately. That would be a pretty powerful use case to be able to check if people are not from sanctioned country. But if they can easily evade it, that's a bit of a problem. Yeah.
Would there be many North Koreans that have another country?
So, in the case of North Koreans, I think most of them are like diplomatic passport. So, yeah, but like, as far as but like most of them are diplomats and well, or like spy or whatever.
So it's easy to say. More people then. It's easy.
So it's easy to have from Iran, for example, and from another country.
Yeah, so but you have to assume that the person doesn't have another passport, which is a strong assumption, I would say.
The sanction usually applies to, like, if you're a dual citizen and one of the states is sanctioned, that applies to you, even if you have.
Yeah, so even if you're a citizen of another country that's not sanctioned, as long as you're a citizen of another that is, then you're going to be sanctioned. You know, like the rules for AML in France are very strict, in the sense that even if you're not citizen of Russia, but born in Russia,
wow,
you may be like flagged. So yeah, the rules are like sometimes quite strong.
Yeah. So I have another doubt. Okay, so essentially here we have two level of problem, orthogonal problem. One problem is that the fact that the proof can be forged. I mean, that in any case, even if it can be forged as some application, so if I can prove that you have some age, anyway, it's a valid proof that you have some given age, even if this proof can be copied. It cannot be used for online voting, and blah, blah, but anyway. But my issue is the following, that, so if I remember well, RFID problems are deniable, and this is by design of in-house, in the sense that, for example, if I have, if you have a transcript, this transcript can be simulated, so it's like the policeman at the check-in the airport is convinced that I am this person, but he cannot send this information to someone else to prove that you passed the check control. It's like, think about interactive Schnorr proof. If you interactive in an interactive Schnorr proof, you are convinced that I have a given age, but you cannot copy this, you cannot give this transcript to somebody else because this transcript is simulatable. So this would be an issue because, I mean, it would be not even, I don't know, I don't remember the details of, but usually RFID protocol are simulatable. So did you consider this?
No, I haven't studied the hardware that much on this, just yet.
So what you actually would want to have is a designated verifier proof, so that only the legitimate recipient is convinced by your snark, but if they forward it, then basically no other entity will be trusting the snark, which is challenging to...
I'm not talking about snark, I'm talking about the wait, ADAS passport, if I have a signature, this is a non-interactive signature. Interactive signature is, cannot be denied by design, you know, you can, but instead interactive protocol, I mean, interactive RFID protocol usually is deniable. So it's like sending some first message, you reply with some challenge, and the three-move protocol is simulatable. So it's completely different set, and this is by design. You should just convince the policeman at the security check. He's convinced because he's the one to send the challenge. But the transcript itself cannot convince another person, because this person said, oh, you could have run the simulator, for example.
You're specifically speaking about interactive protocol.
The RFID protocol itself that is used in the communication, for example, with between the passport and the reader.
Yeah. Okay. But this is specifically for like more like border control, like in this case, like because online verification, I think it should be fine, like the assumption. It's like, all right. We don't have time for another question. No. Just real quick.
Okay, so last question. How do you deal with the revocation? Like, how do you check that the passport was not revoked?
So like this is the revocation list that was mentioned before, so we need to check it. Sometimes they have like the entire revocation list available, so you can make
so this is public, right?
No, always. So, sometimes it is. When it is, you can make a proper proof. When it's not, then you have a bit of a problem. You assume that the document was not revoked. So.
And can you check it after the ZK, after the snark was created? Can you validate that?
Well, if you you would need the document number. So if you do it after the proof generation, and you have the document number as a private input, then you wouldn't know. So you would need to generate it at the same time. Otherwise, you wouldn't be able to. Right. Just gonna leave this if you want to stay in touch.